Anytime we come across some body of mass, we've been simplifying it visually, and we've been treating it as a point mass, or a particle with all of the body's mass located at a point. You may have been wondering if everything we're doing really doesn't apply to any real-world scenario because we've been making such a crazy assumption. In this video, we'll talk about the concept of center of mass and speak to those worries. So for example, what if we wanted to calculate the motion of this waffle? Going by the procedure that we've been following for every lecture up to this point, we would just treat this waffle as some block, right? And then we would assume all of the motion is happening to its center of mass. We're treating it visually as some block, and then for our equations, we're just treating it as a point particle or a point mass. So all of its mass exists right at the center of mass, maybe somewhere right around there, but I'm not sure. Because it's a complex volume with some varying mass distribution. So is what we've been doing valid at all? Or is everything pretty far off from reality because we're not taking into account the details? So let's say we have some system of particles with masses m1, m2, and m3, and so on, right? Dot, dot, dot. We define a coordinate system, and each particle exists at coordinates x1, y1, x2, y2, x3, y3, and so on, right? So each particle has a mass and a position. The center of mass of the system is at the point x, cm for center of mass, y, cm. And x, cm, and y, cm are x, I'll start over here, x, cm is equal to m1, x1 plus m2, x2 plus m3, x3, plus dot, dot, dot. And that's all over m1 plus m2 plus m3, the total mass of the system, however many there are. In more compact form, we would write this as the sum over I of mi xi over the sum over I of mi. There we go. And for YCM, it's the same. Just replace the x's with y's. Yeah? So that is how you find the center of mass in each dimension of your coordinate system that you've established. In terms of the position vector, r, so r, cm, right? So r is just a total position vector made up of components of x and y. So RCM is equal to m1 r1 plus m2 r2 plus m3 r3 and so on, divided by the total mass again, plus m2 m3 plus dot, dot, dot. Nothing changes down there. And in more compact form, this would be equal to the sum over I of mi r, position vector I, over the sum over I, the number of particles there are, mi. The center of mass is essentially the mass-weighted average position of the particles in statistics terms. For solid bodies with a continuous distribution of matter, we can say a few things about special cases. For a homogeneous body that has a geometric center, like the center of a cube, sphere, or cylinder, the geometric center is also the center of mass of the body. A homogeneous body is a body that has its matter equally distributed throughout its volume. Whenever a body has an axis of symmetry, this is number 2, whenever a body has an axis of symmetry like a disk, the center of mass of the body lies on this axis. And 3, there is nothing saying that the center of mass of the body has to lie within its volume. A donut's center of mass is in the center of its hole, so it's not within the volume of its body. And this is the basis for a lot of physics toys that seem to break the brain. They're balancing in ways that it doesn't seem like they should be able to balance. Well, their center of mass is just outside of its volume. So it's hard to visually understand when we look at it, but the physics makes sense. So if we take the time derivative of this position vector r of the center of mass, so dr cm dt, you get vcm is equal to m1 v1 plus m2 v2 plus m3 v3 and so on. And that's still over the total mass, m1 plus m2 plus m3, right? And then let's call the total mass, this, all of it, capital M, right? So we'll say it's all over capital M. The total mass. And then let's bring the total mass over here. So then you have M VCM is equal to M1 V1 plus M2 V2 plus M3 V3 plus yada yada yada. What is this? What are these quantities? M times V, mass times velocity. Well, that is just momentum. And since we're including the entire system, that's what the dot 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 is for, then we're left with this being just the total momentum of the system. And so thereby, the momentum of a system is equal to its total mass times the velocity of the center of mass of that system. Here. This is a big deal. This means that even if the mass of a body is spread out over some weird volume, we can still treat all of its mass as existing at the center of its mass, at its center of mass, and calculate its motion just the same. So even if we have a cow, right, or a waffle with some odd geometry, an odd distribution of mass, we can still treat its entire mass as existing at its center of mass and come out with the same motion results. And so our seemingly wild assumption of treating all these bodies as point masses existing at their center of mass, seemingly wild, it wasn't too wild of an assumption after all. So there's some interesting consequences that come out of this result here, this idea. And they're hinted at by the donut. When a body or a collection of particles is acted on by external forces, the center of mass moves just as though all the mass were concentrated at that point and it were acted on by a net force equal to the sum of the external forces on the system. Right? That's what we were just talking about. We could treat all the mass at the center of mass. But just like the donut, nothing is saying that the center of mass of the system lies within the volume of any one object within that system. You're putting it together. When you fire an exploding firework up into the sky, the firework explodes into many pieces, but the center of mass of the system continues on the exact same trajectory as if the firework did not explode. So let me draw this here. Okay. Firework, firework, moments of time, firework. big explosion. Right? Big explosion. So it breaks up, and now the firework, let's just simplify it and say it's in two different pieces. That would be the trajectory it would continue on if it didn't explode. But instead, it breaks up into this and this. Two pieces that follow these trajectories. Broken firework, broken firework, broken firework. And this one, broken firework, here, here. So the two pieces follow two different trajectories, and we're just handling if it's split in half, but if it's split in a million pieces, it would seem like a very, very complex problem. But the center of mass, if you consider both of these as existing as the particles of a total system, the center of mass of that total system is continuing on the same trajectory as if the firework did not break up. So after the shell explodes, the two fragments follow individual trajectories. The center of mass continues to follow the shell's original trajectory because this is the center of the mass. Right? Cm, Cm, and Cm. And here, the Cm was within it. Cm. So you can kind of extrapolate out to more and more complex scenarios. It really gives you a sense of what total system momentum is. All right, so next we're going to talk about rocket propulsion, which is a fantastic application of conservation of momentum in the case where mass is changing as the system goes along.